Hi, my name is Rick Higas. I'm from High Point, North Carolina, and this is my 16th summit.
I've been to
7 times so far.
This is my 6th past summit, and I'm super excited to be here.
There's so much content.
Really wait for the whole year for this moment.
I can learn, share my knowledge.
A lot of networking, meet new people.
All the people I've met, I'm now very good friends with, but they're also great resources.
Such a great community.
Last year was amazing, and I can't wait to go this year again.
I'm looking forward to the best past summit ever.
Please welcome PASS Executive Vice President, Finance and Governance, Grant Fritchie.
Good morning. Hey, you made it to day 2. Congrats. All right, so since Past Summit 2017 started, there's been 79 sessions representing 185 hours of knowledge sharing from industry experts. That's a lot of learning. Now, hopefully, most of you made it to last night's exhibitor reception. We really appreciate our exhibitors, and I hope you take advantage of the knowledge sharing that they have. Now, as I transition from my role as the Executive Vice President and the past President for 2018, I'm excited for the progress that we've had, for what the future has in store, and for where PASS is headed as an organization. It's a real honor to be part of that. Now, over the last 19 years, PASS has expanded to 92% global representation, including 180 countries with a total of 250,000 members. In the coming year, we plan on expanding our reach and include even more regions and data professionals from around the world. Now, as we look to grow our membership, PASS recognizes that none of this would be possible without you. Here today we have DBAs. No? We have developers. Yeah, architects. BI and analytic practitioners. Analysts. IT pros. Technical directors. Managers. Yeah, data scientists. And the rest of you. We're more committed than ever to ensuring that we're providing each and every one of you with awesome educational opportunities that will help you grow in your career. Being involved with PASS has had a major impact on me, both professionally in my career as a DBA and personally. And I look forward to ensuring that these opportunities are available for our members. And it's important we take a few minutes to discuss the financial health of the organization. As a not-for-profit, the funds we raise are cycled right back into the resources we provide to our members. And it's events like the PASS Summit that help our organization generate the revenue it needs to grow the existing programs and introduce new ones in the future. PASS Summit continues to be our biggest revenue-generating event at $7.9 million last year. That represents 93% of our overall revenues, and this is followed by advertising and sponsorship. So where are we spending our money? As you can see, we've injected $6.4 million back into the community, with a lot of that coming back into PASS Summit. In keeping with our commitment to building a worldwide audience, 39.1% of last year's spend was invested globally, and this number is increasing year over year. The PASS community has also recently elected our most regionally diverse board ever. So I'm excited to see the effect of this global representation on the board and within the community. We've also achieved a lot of global milestones with our virtual groups. We have 30 virtual groups with over 174,000 members in 9 different languages. This year we will host 4 24 hours of PASS events and 5 PASS marathons, bringing fresh and relevant content directly to our members worldwide. But we're not stopping there. There's a lot more we want to achieve for the community. As we get further into the fiscal year, we'll continue investing in programs and educational opportunities that align with the vision for the organization to help all our members access the resources they need to achieve their career goals. And last, but certainly not least, have some fun. We're all here to learn, but being at PASS Summit's a unique opportunity to meet up with leading data professionals from around the world. So attend the networking events, make new connections. Believe me, we got a whole ton of fun events yet to come. Check out one of the vendor parties tonight, or register for Pass's game night. If you see me anywhere, come over and say hi. Now, I'd like to welcome to our stage Vice President for Marketing, Denise McInerney.
Thank you, Grant, and good morning, everyone. There we go. I hope you've all been enjoying your experience so far and are making new connections with data professionals from around the world. Speaking of around the world, this truly is a global experience. We have 2,176 viewers from 56 countries tuning into Pass TV. We're glad you can join us and be part of this special event. Yay, yay for Pass TV. And I know that many of you can't get to all the sessions that you'd like to see, but you can purchase those session recordings at the registration desk, so don't forget to do that. When I first joined Pass in 2002, I really had no idea how that decision would end up shaping my career. All I knew was that there was a regional event I was interested in attending. After being impressed with what I learned at that seminar, I decided to attend my first Pass Summit. I gained so much technical knowledge and made so many new connections that first year that I was really hooked. My first volunteer role was on the Pass Summit Program Committee. I became active in local and virtual groups, and in 2012, I joined the Pass Board, which ultimately led to my current role as Vice President of Marketing for Pass. I truly feel very fortunate to have been able to serve this global community and get to know so many of you through my 6 years on the Pass Board. And just as volunteering for Pass changed my career, it can change many of yours. Our organization and this event would not exist without the hard work of our committed volunteers. Your contributions help your fellow data professionals to learn, excel in their careers, and in return, you get that support whenever you need it. Now, every year, we like to recognize a member of our community who has exemplified the spirit of Pass by going above and beyond to help their fellow community members. This year's winner has volunteered across Pass local groups, SQL Saturdays, virtual events. He has served on the Pass Program Committee as a regional mentor and as part of the Pass Buddy program supporting new members of our community. He's dedicated untold hours to the Pass organization, and I am honored to present the 2017 Passion Award to Roberto Fonseca. Thank you, Roberto. Now, one of the important ways we ensure Pass is moving in the right direction is by reaching out to our community and getting your feedback. This year, we completed our second annual membership survey, which we reviewed and leveraged for our planning for the current year. These surveys have given us invaluable insights into the needs of our members, and we use this to help inform everything you see here this week. From changing the structure of our session tracks to how we curate the best possible content, these decisions were informed by you, the community, and are foundational to our success. But we are far from done for making Pass everything it can be. So please, take the time to complete your session evaluations. That feedback helps shape the future of this organization. And you can also give your feedback at the board Q&A tomorrow. Come ask your questions, learn about our progress, and members of the board will also be at the Pass Community Zone at various times throughout the week. And if you see any of us walking around, as Grant just offered, please stop by, talk to us, give us your feedback, share your thoughts. Now, did you all enjoy the exhibitor reception last night? Yeah, it was good, right? Well, as we have more events to come, so please take advantage of all the activities and networking opportunities. Today, we will be hosting the 15th annual Women in Technology Luncheon, featuring Heather Ritchie from Nokia. Her talk is entitled, He Says, She Says, Bridging the Communication Gaps that Prevent Great Ideas from Being Heard. And, backed by popular demand, is our Speaker Idol contest. Watch as speakers put their skills to the test and compete for a session at PASS Summit 2018. And speaking of PASS Summit 2018, I am pleased to announce that registration for next year's event is now open. Our event gets better every year. Yeah, that's right, go register. We hope you can join us. Register today and take advantage of that early bird pricing by visiting passsummit.com. And now I'm very excited to introduce today's keynote speaker, Rimma Nehme. Rimma is the Group Product Manager for Azure Cosmos DB at Microsoft. Prior to this role, she worked at Microsoft Gray Systems Lab and Microsoft Research. She holds a PhD in computer science from Purdue University and an MBA from the University of Chicago. Rimma will share how public clouds are quickly making massive scale computing capabilities available to a growing population of developers and data professionals. Please join me in giving a warm welcome to Rimma Nehme.
Thank you. Good morning, everyone. How's everybody doing? Good, 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 good. So I am really, really pleased I'm back. Thank you again, the community, for inviting me back here to be the keynote speaker on day number 2 again. I am a big fan of PASS community. As you all know, I follow you on Twitter as well. I know what you guys are up to. This is going to be a great keynote. And I am super excited to be back. I also have to say, even though I've done these for a number of times, I'm still also a little bit nervous. But I think there's a lot of interesting material to cover, and hopefully you'll get to appreciate it as well. The way I always put it, the day number 2 keynote is very different from day number 1. And the disclaimer is, this is going to be a more technical talk. It will be educational, at times controversial, at times funny. Thomas LaRocque wrote a blog, 42 Things You Should Never Ever Say to a DBA. I will probably violate about half of them today. Brand Ozer likes to deadsplain things sometimes. I will try to momsplain a few core fundamental principles here. So, remember PASS 2014? That was my first keynote here with this community, and it was, what's a cloud database? Here we are, it's PASS 2017, and today we're gonna go deep inside of one of the, what I would say, best cloud databases. Obviously I'm biased, but you have to take that with a grain of salt a little bit. Today we're going to go and cover Azure Cosmos DB, the internals, why it was designed the way it was designed, what were some of the problems, key problems that the product is trying to solve, and how does it actually go about solving it. So enough of this stuff. You came here to learn about globally distributed databases. So one of the key questions that frequently get asked, do we really, really need another database? If you look at the list on DB Engine side, if you look at the list of all of the open source software technologies out there, there are plenty. And every month or so, you will hear about yet another database engine. The way I view it, it's actually a wrong question to ask. If you look at the rising modern data problems, if you're looking at the rising modern data needs, and most of the production systems today that were designed, quite frankly, in the 1970s, 1980s, there is a little bit of a chasm. There is this gap. So the modern data trends and the needs are calling for a new way of addressing these fundamental problems that are rising today. What are they? One of the interesting statistics that I've actually came across was 90% of the world's data was created in the last 2 years alone. That's pretty shocking, actually. And if you look at the projected growth of the data in the next 3 to 5 years, it's estimated to be anywhere between 50x to 150x. And largely, this data will come from sensors, devices, social media, voice over IP, and so forth and so on. Another trend that we're seeing is global. You know, many of you have read the book by Thomas Friedman, The World is Flat. So even though you could be a little startup in Israel or in Eastern Europe, your users could be anywhere across the globe, in North America, in Southeast Asia, in Australia. Another trend is actually data is big. And by big, I'm talking about not just a few terabytes, but we're seeing trends of, you know, even a little company, a little medium-sized business processing data in the hundreds of terabytes, going into petabyte territory, and in the future also going into exabytes. Data is also live. You know, every 60 seconds, 204 million emails is being generated. If you are using WhatsApp, 347,000 WhatsApp photos are being shared, 260,000 Instagram posts, and that's every 60 seconds. Multiplied by 60, multiplied by 24, multiplied by 365, data becomes very, very, very big. Data is also interconnected. Sometimes the fact that you're buying a Coke in Seattle, Washington could actually have consequences somewhere else in Southeast Asia or maybe in another geographical region. There's this very interesting concept in mathematics, in chaos theory, called the butterfly effect. And I call it, this is the butterfly effect of data as well. As I mentioned also, the data is growing. So by some of the projected estimates, we're currently already are experiencing somewhere about 125 exabytes of data. That's a lot of zeros. And that trend will only continue growing. Companies, startups, even students, research institutions, they're all looking for ways of extracting information out of that data. Companies are looking to monetize on that data, either to optimize their operations or try to find that something special from that data that will differentiate them in either their industry or their vertical. Another trend that we're seeing is also the balance of power continues to shift from structured to unstructured data. So roughly today, 80% of the business relevant information originates in the unstructured form. And that balance will also continue to shift going forward as well. Another trend is, when you're taking, for instance, Databases 101 course, the very first thing that you learn is that you never push the data to your computation. You always try to push the computation close to your data. So by virtue of users who are generating data being anywhere across the globe, you obviously also want to try to push the computation close to where the data gets produced. So these are some of the trends that we are observing and experiencing today. So in 2014, I coined this term, earthly database. The key thing, and this is not actually a really controversial observation. If you take an earthly database and you put it on the cloud, by virtue of cloud being everywhere, having the presence everywhere across the globe, it just simply will not work to try to address these trends and do so well. So fundamentally, when you're dealing with the distributed systems, which in this case, that's what we're talking about, you need to deal with things intrinsically different. And there was this seminal paper in 1994 that actually also talked about that distributed systems fundamentally require different architectures. And in this case, we are talking about distributed databases. And adding further, we're talking about globally distributed databases. So the story goes as such. In 2010, an engineer inside Microsoft, his name is Dharma Shukla, observed that, and he also basically identified saying, we need to have a fundamentally different architecture to try to address these fundamental needs of dealing with data at the globally distributed scale and be able to solve these problems and do so well. So this is how Project Florence was born. And Project Florence is the blueprint of what is known today as Azure Cosmos DB. It was a team of, a very, very small team, started with Dharma, and then a couple of engineers who joined him, and then it grew over a period of time, that built that basically originated this system called Azure Cosmos DB. It was also one of the exemplary partnerships between Microsoft Research and Azure team as well. So why Florence also? You know, there's actually two stories behind it. Number one is, if you've ever visited Florence, Italy, there is this very, very famous dome. It was done by one of the founding fathers of the Renaissance. That's where the Renaissance was started, by Filippo Brunelleschi. And he's deemed as one of the architects of the Renaissance because he invented this, this new concept of designing architectures that became the blueprint for many of the other following up designs. But there's another story behind it. Actually, Dharma at the time was on the vacation, and he took the laptop with him, and that's where the first version of Project Florence, Azure Cosmos DB, actually started working. So that just gives you also the idea how Microsoft engineers take vacations. So the goal was, behind Project Florence, how can we natively build a cloud database? One of the things that the project was designed to do was try to actually address the needs of the first-party customers inside Microsoft. So at the time, you know, there were internal teams inside Microsoft like Xbox, Bing, Office 365, Universal Store. They were building large-scale consumer applications because by virtue of Microsoft being a global company, they had users everywhere, they had stateless front ends everywhere, and they needed the database backend that would scale with their needs. They tried, obviously, you know, the typical, what we call earthly databases that didn't quite work for them. They also tried building something on their own, and they ended up spending most of their time on the back end rather than actually addressing the needs of their app. So this is how Project Florence was born, to first try to address the needs of the internal Microsoft customers. And there was a set of requirements, basic set of requirements that were laid out in order to tackle them, how should the system be designed? And they were the following. Number one was the turnkey global distribution. And this is by virtue of, again, company being global, applications being global, stateless front ends being global. The database also behind the scene need to be global as well. The second requirement was guaranteed low latency at the 99th percentile and being able to provide it worldwide. The third requirement was guaranteed high availability within a particular region and also across the regions. The fourth one was guaranteed consistency, and we'll talk about consistency pretty deeply in this talk. The fifth one was elastically scale throughput and storage at any time, on demand, and globally. So this is, you know, the whole core value promise of the cloud, you know, being everywhere across the globe, and being able, for a user, for a customer, for a developer to be able to come in, ask for the resources that you want, being able to use them, and then scale them back down. So translating it into the database backend capabilities as well. Comprehensive SLAs. So we'll talk about the SLAs as well. Being able to cover not just the high availability, but all of the other dimensions that customers also really, really care about. Operate at low cost. This is actually pretty crucial and pretty important because, you know, again, keeping in mind that the first customers were the first-party customers inside Microsoft, they were already operating on a very, very low margin. So if the database backend becomes really, really costly, you know, we will eat up into their margins as well. So that was actually a pretty core requirement as well. Being able to also iterate and query without worrying about schemas or index management. So this was also a pretty crucial capability because applications evolve. They evolve over time and they evolve very, very, very rapidly. And the last one was provide a variety of data models and API choices. This is to enable developers to, whichever world they're coming in, whichever environment they're coming in, to be able to lower the barriers of adoption of this service. So this was the original set of requirements. You know, how would we build such a system? As a result, it manifested in sort of three core principles that, and how the system actually has evolved. The first one was the global distribution was built from the ground up. That was the core piece of the architecture. The third one was, it was a fully resource-governed stack. And we'll talk about resource governance pretty deeply in this talk, because it's fundamental when you're running an elastic database like Cosmos DB. And the third one is, it was built as a schema-agnostic service. Again, to be able to satisfy the requirements of querying without worrying about schema or index management or data models, and being able to onboard other API models, data models and API languages very, very easily. It's very hard to build any service. You know, being part of this, you know, sort of cloud revolution, it's amazing to watch all the services popping up, you know, so frequently. But I will tell you, it's really, really hard to do it. And especially building a service with such, what I would say, far-reaching capabilities, it is very, very hard. But the way we put it is that if it was easy, everyone would do it. And NASA has this really, really great statement: failure is not an option. And this was actually quite built into the spirit of the team, going how it originated and going forward. So this is how Azure Cosmos DB was born. It is, as of today, as of now, it is used extensively inside Microsoft by all of the internal Microsoft customers as well as externally. It's one of the fastest Azure services on the cloud. It's also a foundational Azure service. That means internally we call it a Ring 0 service. That means it's automatically is available in all of the Azure regions by default. The way we roll out services is typically by rings. So whenever a new region gets added, Ring 0, Ring 1, Ring 2, services typically rolled out by the rings. So this is a Ring 0 service. It's millions of lines of code, mainly C++. So even though externally it's perceived as a relatively new service, it's 7 years in the making. So I've told you how Azure Cosmos DB was born. Here's what it looks like. This is a little bit of a marketing slide, but I think it will give you a big picture of what the service is all about. The foundation of the service is composed of 5 core value propositions. And this is turnkey global distribution, elastic scale out of storage and throughput, and being able to do so independently at any point in time, guaranteed latency at the 99th percentile, 5 well-defined consistency models, comprehensive SLAs. This is what we call the foundation. And on top of that, the service is built to be a multi-model service. It supports key value, it supports document data model, it supports graph. And then on top of that, it's also a multi-API service, trying to meet the developers wherever they are. And we'll go one by one. This picture will become very, very, very clear by the end of the talk. My team likes to call it, it's a house picture. You know, there's a foundation at the bottom. This is what makes it really, really stand out. Then we have all the kinds of different rooms for different data models, and then we have all the doors to welcome everybody by virtue of multi-API approach. So let's talk about fine-grained multi-tenancy, because that's actually very, very important when you're building a cloud service. In particular, when you're building a stateful service like Cosmos DB or any other database service. It cannot be an afterthought. So if you look, for instance, from the dimension from left to right, and I mentioned about this concept in 2014 when I was talking about cloud databases. On the one hand, you can take a physical resource, like a cluster, and you can dedicate it to a single tenant. And by a single tenant, I mean a customer or a database. You can also go one level further, and you can take entire machine and dedicate it to a single tenant. You can go one level further, and you can take the entire machine and dedicate it to many, many homogeneous tenants. They run similar workloads and get the similar system guarantees. Now, the final step is, the final level of granularity is that you can actually take the entire machine and divide it among very, very heterogeneous tenants, guarantee them predictable performance, guarantee the resource isolation, and provide the best security. So if you remember the 2014 talk, this is what you need to do. Remember the analogy of the house? You can either own the house all by yourself, or you can go and rent the rooms out. So the same thing could be applied to the database workloads. And they can be applied, basically, you can take a server, you can virtualize it, and then you can divide it among the various tenants. with respect to the global distribution, remember I mentioned to you that it's a foundational Ring 0 service. So today, Azure is announced to have 42 regions worldwide. 36 regions are operational and 6 are being built out. So Azure Cosmos DB is available in all of these regions. What that means is you can take your database and you can literally span it across the entire world. So making your data truly planet scale. What does it look like? And I'll take you on the tiny, tiny, mini virtual tour of the data centers. And I think I did that in 2014 as well. So for instance, this is Amsterdam region. Your data lives there. This is Cheyenne, Wyoming. Your data could be living here. There are some people from Wyoming. This is Quincy, Washington, right here nearby as well. Your data could be here. Another view of the Quincy, Washington. This is what it looks like inside. This is not how every single region or every single data center, what it looks like inside, but it gives you an idea. The key thing here to remember is that you can take your table, and parts of that table could be living in all of these geographical locations. But as a user, you get this single system image for all of these globally distributed resources, regardless of whether you are using a table or a graph or a collection of documents. You view it as one single entity, as if it were on your personal laptop. But behind the scene, it's actually distributed across all these geographical locations. It's pretty awesome, right? So let's talk about the resource model a little bit more. So you have a database account. Below the database account, you have a database. All of the system resources, such as user permission, whatnot, is there. The basic concept inside Cosmos DB is what we call a container. And a container is basically representation for the data model, a container of data with a particular data model. So it could be a table, or it could be a collection of documents, or it could be a graph. And below it, there could be other user-defined resources, everything from stored procedures to triggers to UDFs, and so forth and so on. Your database account and database may span multiple clusters, multiple regions. You can scale it in terms of these containers, okay? And so this is basically mapping between the two concepts, and it's designed, again, to scale the throughput and storage independently. And you can do it across these two dimensions to suit your needs. So how is the system designed behind the scene? And again, this is a little bit of a 10,000-foot view. Again, you take the Azure regions spread across the globe. Within the regions, there are data centers. Within the data centers, there are stamps. Within the stamps, there are fault domains. Within the fault domains, there are clusters of machines. If you zoom in on a particular machine inside the cluster, you will see that there are hundreds of tenants on that machine. There are containers, and within the containers, we store the replicas. Replicas, you can think of them as basically partitions, chunks of data co-located with the database engine and a bunch of other components, such as admission control, resource governor, transport protocol as well. And then if you zoom in on the database engine, this is where a lot of what I would call secret saucery came in as well. Everything from specialized indexing techniques in the form of the BW tree, Llama++, query processor, language runtime host, to be able to host various runtime environments such as JavaScript and other runtimes coming in the future, I/O manager, and also, again, resource manager, because, again, resource governance is very, very important. So on any particular cluster, we'll see anywhere between thousands to thousands of tenants. On any machine, you can see hundreds of tenants. And so we need to make sure that none of the tenants are noisy. Nobody does any crazy stuff. Another concept that is very, very important in any scale-out system is the concept of partitioning, okay? So let me go and dive a little bit deeper as to how Cosmos DB solves this problem. So you take the tenants, again, create tables or collections of graphs. These are what we call containers of data. Behind the scene, these containers of data are partitioned, and we call them as resource partitions. If you zoom in on any one of those resource partitions, they basically are comprised of 4 replicas. We call them a replica set. And this is like what we call a tiny, tiny Lego block out of which you can create pretty sophisticated things. It's a consistent and highly available and resource governance coordination primitive. It uniquely belongs to a tenant, And it consists of a replica set, with each replica hosting an instance of database engine. So each one of them is like a very, very pretty smart construct. So out of those partitions, you can go then create partition sets. And so these partition sets then can span clusters, federations, data centers, regions. You can overlay all kinds of various topologies out of these partition sets. Everything from a chain to a tree to a hub spoke, to implement various types of very sophisticated coordination protocols spanning across multiple regions across pretty much the entire planet. Behind the scene, you need to make sure that various applications are working really, really well. For instance, when you need to perform the split, when you need to perform the merge, when you need to go and copy one particular partition or partition set, it all needs to be very, very robust. But the key takeaways from this slide is you have the partition, which is your teeny tiny Lego block. Out of those partitions, you can build the partition sets of various topologies to go and implement all kinds of distributed protocols. So what are some of the best practices? Because partitioning is so core fundamental to any scale-out system, there are some best practices to follow. So what are they? Number one is you always want to select a partition key that provides even distribution. That's a no-brainer. You obviously don't want come up with a partition key, like for instance gender, and then have a very, very skewed representation in one of the partitions. It's not just a question of performance and scale out, it's also a question of the cost. And when we talk about the billing model, I'll describe you what it actually means. When you provision the throughput is typically evenly divided across all of those partitions. So if you have one partition that is hot, it's gonna go and eat up all of that throughput, while other partitions are sitting idle. And so in that respect, this is capacity that is being unutilized, and this is the capacity that you might be paying money for, especially in the cloud environment. The second best practice is using location-aware partition key for access locality. So if, for instance, you have part of your application has only customers in a particular geographical location, you might want to potentially just partition it based on that geolocale and localize the workloads. The third one is you want to select a partition key which can be a transaction scope. So Cosmos DB supports today ACID transactions at the scope of a partition. So if you could co-locate all of your data within that partition where you need that ACID property, that will give it to you. If you end up spreading it across multiple partitions, that property will be lost. And then the fourth best practice is you don't want to use the timestamp for write-heavy workloads. Typically, you would want to use time ranges, like an hour or week or a month, to, again, even out your distribution of data. So again, in summary, your resource model, there are resources. They are identified typically by their logical and stable URIs. Internally inside the system, they're represented by JSON. They are partitioned, and they span across machines and clusters and federations. And then you have this physical representation of partitioning model, which is a grid partitioning model. And the way you could view it within the region, it's locally distributed. Typically, we would have multiple partitions within the region. And then as you're adding new regions to your database, it will be what we call globally distributed or vertically distributed. Okay? So this is the logical mapping combined with the physical mapping. So let's dive into the core capabilities. Now that we've covered sort of the basics, what is the resource model, what are the basic building blocks, Lego blocks, let's look what makes the service really, really stand out and how did we do it. So the first thing is the global distribution turnkey capability. And it's literally adding the regions with a click away. What that means is you can come to an Azure portal, you can see the map of the entire world and pick the regions where you want your data to be. And then select them, click a save button, and that's it. The data gets seamlessly replicated behind the scene and becomes available for querying. So you don't have to deal with the data centers, you don't have to deal with clusters, you don't have to deal with VMs, you don't have to deal with cores, none of that. The analogy that I like to give sometimes, it's like driving a car. When you come to a car, you turn on the key and it gets you from point A to point B. You don't need to know how it works under the hood. You could go look and see how the engine is working, but you don't have to. And it's sort of a similar analogy with respect to a global distribution in this case. As you're adding and removing, you can add and remove regions at any point in time. As you're adding and removing your regions, your application does not need to be redeployed. It continues to be highly available at all of these times. The connection between the application and the database is typically logical. And this being able to add and remove regions without affecting your application is enabled by what we call the multi-homing API capability behind the scene. You have the capability of also physically connect to the endpoint inside the region. If you want to go and minimize on the latency even further, you have that option. But typically, most customers go with the logical connection. Another cool capability is that you can actually go and associate priorities with all of these regions. So in the unlikely event of, for instance, regional outage or a failover, the failover will occur in the order of those priorities. And you can basically drag and drop, add more regions, and then reorder them at any point in time to change the priority. The cool thing that we've added to the service is actually for customers and for developers to be able to come and simulate a regional outage. Don't go crazy with it though, guys. Yeah. So you can come in, you can literally come and simulate the region failure and just see how the service will react and how your mission critical application will actually react to that as well. So you can test the entire high availability of your entire application stack, not just the database. Another capability, by sheer virtue of the fact that it is a globally distributed database service, is being able to provide geofencing. Obviously, if you come from Europe or from any other parts of the world, sometimes there could be regulations where the data has to be physically present only within those regions. So we've added this capability of being able to geofence the data based on the particular policy. So if the data needs to stay within Europe or Australia for whatever requirements that your application needs to address, we provide that capability as well. How does the always on work? So remember, because by virtue of this partitioning, having multiple replicas in the replica set, your application and your data will always be on. So for instance, one use case scenario, let's assume one of the replicas goes down. What happens? Your application will be unaffected. It will just basically go to another replica in that partition. Let's assume the entire partition goes down. What happens? Again, by virtue of using this intelligent client of the Cosmos DB, it will just go to a partition in another region. Let's assume in the unlikely event the entire region goes down. Again, the application will continuously keep on getting their data by just basically going and getting the data from another region. So your data is always on. It's always highly available. Another pattern that we see frequently being used and being of interest is this active writers and active readers, where you should be able to go and update, write, and read your data in any region. So today we support a turnkey single and multi-master topology at the database account level, but something that we're working on is being able to push it down even further at the final granularity level, to be able to enable a multi-master topology at the partition key range level. So the true active pattern. And this is something that will come a little bit later on. Online backups, how do they work? So typically, again, if you take your container of data, you have your partitions, within the partitions you have your replica sets. Typically, we take periodic full backups. They're stored in the Azure Blob storage, localized to every geographical region. The key capability, and this is something that I wanted to mention explicitly, is that it's really intended for, oops, I deleted my data. It's not really for the disaster recovery. For the disaster GUDR, this is where you adding multiple regions capability, having 4 replicas. This is how the service addresses those needs. But if sometimes it happens by mistake, people delete the data, this is where the backups will become very, very handy. So let's dive into the second capability, the elastic scale-out of storage and throughput. And as I mentioned before, the key capability here is being able to scale your backend, your database backend, as your data size grows, and also being able to independently scale your throughput. Why is this so important? Well, you know, it's pretty obvious. It could be you start out, for instance, with just a small amount of data. Over time, you'll keep on adding more and more data. And so instead of you, once you hit the limit, going and getting another database or moving to a more scalable database, your backend will seamlessly scale as your data size grows. Another requirement is typically if you are building an application that is what we call polyglot in nature, it's dealing with transactional data, web content data, maybe machine data. These segments of data typically have very different data size requirements. So transactional data tends to be a little bit small in size. Web and content data tends to be a little bit larger. Social and machine-generated data tends to be pretty explosive because, you know, IoT devices are generating data all day long. So the system is designed to independently scale behind the scene for both storage and the throughput needs. We do this completely transparent partition side management as your data size grows or as you increase your throughput. And we do it again within the region, across the regions as needed. Behind the scene, it's an SSD storage backend, and this is designed to make the latencies to be very, very low, and I'll talk about it in a couple of minutes about our latency SLAs. With respect to this throughput, the idea and the use case scenario here is if you're building an application, again, depending on the volume of your users who are interacting with the application, depending on the geographical locale, you might encounter the situation where, for instance, at 9 p.m. Pacific, you will have less volume in Chicago and more volume on the western part of the US. So you might want to go and adjust the throughput and increase it where there is more volume. Now, let's assume a little bit later on, more in the day when it's daytime in Chicago, but people on the Pacific are, I don't know, still asleep. You might, again, dynamically adjust the throughput so that you can satisfy the volume. So again, it's designed, the backend is designed to elastically scale the throughput from just a few requests per second to hundreds of millions of requests per second. So how does it actually work? Behind the scene, we have this concept of RUs, or request units, and many of you, if you're working with other cloud services, you've encountered anything from DTUs to DWUs from all kinds of currencies. So the currency in Cosmos DB world is called RU. It stands for request units. I call it, it's the Bitcoin of Cosmos DB world, okay? So the concept idea there is that all of the resources, the RU basically abstracts a chunk of physical resources on a machine. For instance, a percentage of memory, percentage of CPU, percentage of IOPS. Then all of your operations, all of the database operations that you perform on the service cost you a certain number of RUs. We haven't added the idea of arbitrage yet, so you can't sort of go trade your RUs yet. But you basically, all of your operations, as you're running them, they consume your RUs. Every single replica, when you come in, you provision how many RUs do you need. You can think of them as basically how many transactions per second do you need. You provision it. All of your replicas, and remember the replicas, for the simplicity, is just a partition of your data co-located with the database engine. They get a certain budget of RUs. And then if you go and exceed that budget, you will get rate limited. You'll get a certain return code that will indicate you are exceeding your provision throughput. So at any point in time, you can go and increase your provision throughput, and the system will seamlessly scale and will be able to support more and more transactions per second. And if your volume goes down, you can at any point in time decrease it. So to summarize it, basically, request unit is this rate-based currency, and you provision it at the granularity of a second. So at any point in time, you specify, I want, let's assume, thousands of RUs per second. And it's normalized across various database operations. And the way we basically cost the operations, it's actually pretty sophisticated there. We've run machine learning pipelines to calculate various query costs. So a cost of a query basically will be a combination of scans, index lookups, query memory complexity, any sort of instruction cost overhead. So we've run a bunch of machine learning models on the telemetry. What does it cost us to execute those operations on the actual hardware at place in data centers? And then we can go calibrated the cost model to be able to go and indicate how many RUs will be needed to run a particular operation. Okay, so coming back to the partitioning model. So remember I told you, you can at any point in time either add more data and your backend will scale, but at any point in time you can also change your throughput. So what does actually happen behind the scene? And this is an example of a code sample where you could come in and you specify your throughput. How much do you want? It's literally, you just say offer.throughput and you specify how many RUs do you want. So let's assume you have this situation. You have a container, it's partitioned by the airport. You have two partitions in this case, and each one of them gets half, basically half of the total throughput that you've provisioned. So in this case, you've provisioned 20,000 RUs. Each one of those partitions will get 10K of RUs. Now let's assume you decide to change your throughput. What happens behind the scene? Behind the scene, we'll actually go and add, do the repartitioning, and each one of the partitions will get now 10,000 RUs, and we will be able to go and give you all of that throughput that you've asked for. And so at any point in time, this is where the splitting of these partitions, merging them becomes very, very crucial operation. But again, the system is doing it behind the scene for you. You don't have to worry about it. Let's assume you want to add an additional region. What happens behind the scene? Well, at this point in time, for instance, let's assume at the beginning you were running in West US or West Europe, you add Australia. The best recommendation is that you want to go and add more RUs because you don't want to starve your existing partitions in the existing regions. So at that point in time, you will add another 30,000 RUs to satisfy the requirements of an additional region. And again, those RUs will be spread across all of those partitions. So I wanted to give you a telemetry, for instance. This is one of our customers, a retailer. And they were running on Cosmos DB last year during Black Friday, Cyber Monday, 11/18, 11/30. So you can see over a period of time, they were basically just changing their throughput depending on the needs of their application. At about Black Friday, Cyber Monday, they were running with the throughput of 1 trillion transactions, 1 trillion of RUs, which is 1 trillion transactions per second. This was all the Christmas shopping. And then once the shopping season went down, they just reduced their throughput and then didn't incur any cost. So this is the value, this is the beauty of actually the cloud itself, the fact that you can elastically provision the resources on demand, use them when you need to, and then when you no longer need them, you just turn them off. Rather than doing it, for instance, on premises when you buy a big machine and you incur all of the capex with it. I also wanted to give you some of the visualizations. We've ran it on the telemetry. This is what the multi-tenancy and horizontal partitioning looks like. This is for one of the tenants that is running in the central US region. You can see that they have various workloads that spans hundreds of partitions within that one particular region. This is a snapshot of the telemetry of the internal Microsoft workloads. This is basically workloads running with 3 trillion of RUs consumed in 3 days across 20 Azure regions. The interesting thing is actually something that I forgot to mention at the beginning. For instance, if you've ever interacted with Azure Portal, right? If you already dipped your toe into Azure and you started using some of the services there, when you come to the Azure Portal, that's an application, right? You provide, for instance, your user information, you specify your resource groups, your subscription IDs. It's an application that needs a database behind the scene. So this database is Cosmos DB that is actually powering that application. By sheer virtue of, again, Azure being global itself, it has users everywhere across the globe, it needs low latency experience, and it needs a very scalable database backend. Another zooming into one of the clusters, for instance, in the central US. This is just to show you the actual multi-tenancy at the level of a node. Various nodes have various number of RUs serving different workloads. And if we zoom in on one of the nodes, we can see all of the tenants that are actually running within that node. So they are used in various workloads that are running on just that one particular server. This is zooming out just to show you the multi-tenancy and global distribution at that level. Okay? So the next one is the guaranteed low latency at the 99th percentile. This is very, very important, but you might still ask me, like, why bother? You know, why is latency so important? Well, time is money, you know, that's what Benjamin Franklin always said. So, but from the business point of view, twice as much revenue is being lost. Oh, you guys don't see it. I apologize. There's a little bit of a hiccup. Okay, so let me keep going. Thank you. Well, I was talking to myself. Okay, good. Let me just, okay. So zooming out, multi-tenancy and global distribution. So this is the visualization of showing basically tenants spread across the multi-region RUs consumed across thousands of partitions that are distributed across 3 regions: Central US, East US, and West US. So coming back to the, now there will be a sync between the slides and the actual speaker. So guaranteed low latency at the 99th percentile. This was remember, one of the core requirements right from the beginning when we started building the system. Why is this so important? Time is money. You know, that's what Benjamin Franklin said, but fundamentally, if you look at today's scenario in most of the IT, twice as much revenue is being lost to slow down. So what did the system design to do? You should start reading from this table from the bottoms up. At the 99th percentile, the service will give you less than 10 milliseconds for the reads, measured at 1 kilobyte document size, which is roughly about 80 to 90% of our workload size. And for the writes, we give you less than 15 milliseconds at the 99th percentile. Now, on average, if you look at it, you will observe on the service a latency which is much, much lower, less than 2 milliseconds for reads on average, and less than 6 milliseconds for writes. How is it being accomplished? Remember, I mentioned to you, reads and writes are always served from the local region. We also use SSD backend storage, and the design of the database engine itself was done to be write optimized. We use a latch-free, lock-free database engine to remove any sort of concurrency conflicts. And also, all of your data get automatically indexed by default upon the ingest. This is actually a fundamental difference from, for instance, traditional relational databases, where you typically come in, you specify your schema, you then go and load your data into that schema, then you identify the right set of indices to speed up your workloads. In this case, it's sort of completely the reverse. We don't even ask you, we automatically index all of your data by default, and then serve queries very, very quickly. So this is one of the customer application examples. For instance, in this case, the front end, the application was in West US, but the database region was in the Southeast Asia, and you can see right there in the column the latencies. And this is literally the speed of light. This is, you know, the physics at play. And then all they had to do is basically just add an additional region, and the latency automatically went down to 4 to 5 milliseconds by literally doing nothing except for adding the region. This is example again of the same customer, Black Friday, Cyber Monday. The latency, observe this again, they were running around, again, their busiest shopping season of the year. And again, all of their latencies were less than 10 milliseconds for reads and less than 15 milliseconds for writes. One time, and I'll try this joke on you, sometimes it goes well, sometimes it doesn't. I say Azure Cosmos DB allows you to beat the speed of light. The story goes as follows. For instance, if you have a database in Chicago, right, and you have friends in Paris who want to read your data, if this were a centralized database, if this were not a globally distributed database, typically your friends will come and they will request to read your data and then get the data back. By sheer virtue of, you know, speed of light, geographic distance, sending the request, getting the data back, you will get it in about 80 to 100 milliseconds. With Cosmos DB, it will get you that data in less than 10 milliseconds. Obviously, depending on the consistency models, that's slightly different. different, but that's, that's sort of the story, how Cosmos DB allows you to beat the physics. The fourth one is the 5 well-defined consistency models, and this is actually a pretty fascinating area. Those of you who are familiar with the CAP theorem, this is the beautiful part about how the service addresses the fundamental trade-offs of distributed systems. So how does it go? When you are dealing with any distributed system, whether it's databases or any other system for that matter, typically you're faced with a very fundamental trade-off between availability of your data, consistency of your data, latency, and throughput. So for instance, if this were a centralized database, all of the requests that would be coming from anywhere in the world, they will be just basically reading and writing against the primary copy. With globally distributed databases, typically you would go geo-replicate your data, get both performance, fault tolerance, high availability, and so forth and so on. And clients will read and write the data locally at the very low latency. But problems, failures are inevitable to happen. So what happens if, for instance, C can't communicate with other replicas, and maybe customers are making updates to other replicas happening across the globe? How should you serve your data? What are the consistency guarantees that you're giving? If you're making the updates to your data in regions A and B, but your application is reading the data from the region C, should you wait to make sure that all of the data is all synchronized, updated, and you get the latest, freshest data ever? This is the fundamental trade-off that the CAP theorem describes. Basically, do you want to go for strong consistency, or do you want to go for eventual consistency? And so we call it, basically, do you want to have a red pill or a blue pill? And this is the state of most of the commercial databases today. If you come, for instance, to the relational databases, they typically give you a perfect consistency. And what that means is basically they will not serve the data until the entire quorum is in the agreement, which could be happening with the updates all across the globe, and then they serve you the data. And that comes at the price of the higher latency and lower availability, because until your entire quorum agrees, you can't see that data. So your application is basically sitting and thinking, okay, my data is not available. On the other hand, the whole movement of the NoSQL systems typically said, forget about consistency. We're going to focus on the availability of our data. We'll serve it to you as fast as we possibly can. No guarantees about consistency, but you will get your data no matter what. So this is sort of the current state of the world. But real-world consistency is not a binary choice. These are pretty two strong binary choices, very, very extreme in nature. So there are other consistency levels, and the very frequent question is like what? Somewhat consistent and whatnot. If you look at the research literature, this is what we call, there is a wild west of consistency models. A lot of PhD students have actually written PhD dissertations on trying to navigate the spectrum between these two binary choices: perf, consistency versus availability and throughput. And actually, one of the papers that I recommend all of you to read, if for nothing else, you might enjoy just the baseball analogy. There is this very, very interesting paper called Replicated Data Consistency Explained Through Baseball. And the author, Doug Terry, who used to be at Microsoft, he also motivates the needs using real-world examples from baseball, so many people could relate, how depending on who you are in the game, you might get value out of the various consistency models. And so I actually highly recommend for you to read it. But the fundamental thing is, again, given this very, very fundamental trade-off between consistency and availability and latency, the engineers asked a very simple question. Can we pick out some intermediate consistency models that are useful, easy to configure, programmable? It also represents a very, very clear trade-off between these very fundamental choices that you're faced with, and also provide the SLAs behind it. And that's how Cosmos DB tried to address this problem. So in addition to the strong and eventual consistency, which is what traditional relational databases give you, or traditional NoSQL systems give you, the system also gives you 3 intermediate consistency levels: bounded staleness, session consistency model, and consistent prefix. And the semantics there, with the bounded staleness, you basically specify the bound for your staleness of your data. How many, for instance, you specify the key prefix, how many writes your reads will lag behind. The session consistency model gives you monotonic reads and writes with respect to your local region. so you get the perfectly consistent data local to your geographical location. And then consistent prefix gives you guarantees that when the updates are applied, the prefix is guaranteed to be consistent. So there are no gaps. If you make the updates 1, 2, 3, 4, 5, and we return to you 1, 2, 3, there are no gaps in that prefix. So how do we also go about it? When you're dealing with such complex systems and with so many knobs, so many different various pieces to go with, we use the TLA plus specs to precisely specify consistency models and describe what would happen and how to address it. Those of you who don't know what it is, I will play a video by Leslie Lamport, who was actually pretty fundamentally very phenomenal figure and very important in how the system was designed. Let me play this video. 1 second. I hope it will work because... So those of you who don't know, Leslie Lamport is one of the Turing Award winners. And he is famously known for Paxos algorithm, and he was one of the fundamental fathers of some of the core design principles that we use in the stack. Let me try to see if it will play. It might not. Well, it didn't. If one of the things, we have a blog, and you guys can watch that video after the keynote. But one of the things I wanted to I think it's fine. We can skip the video. Can I have the slides back? Thank you. But coming back to the consistency models. So this is actually a very interesting area because it's actually some of the things that we've noticed that we could monetize on. So we've operationalized these 5 consistency models, and we're sitting and we're watching. How are customers using them? Are they useful? Can they reason about them? Can they make sense out of them? And so I'm actually showing you some of the things from the operational telemetry where based on the real-time feeds that we're getting from the operational clusters, only 3% use strong consistency, 4% use eventual, and more than 93% are using actually these intermediate consistency models. This is something that is not available in any other system, and the signal is that there is a clear value. Now, when it comes to the market for programmable consistency, notice also that depending on consistency model that you specify, you might need to perform a lot more computational work, and that will cost you a lot more RUs. So then you are faced with a very, very clear trade-off. How much performance do you want? How much availability do you want? How much consistency do you want? And how much are you willing to pay for it? So the trade-offs between these consistency and throughput models can be actually monetized, and this is something that the customers decide upon, what makes the most sense for them. So last but not the least is the comprehensive SLAs, and this one is very, very groundbreaking, is that high availability SLA is not good enough anymore. The way I put it, we are now in the service business, not just a software business. And a true measure of any service happens to be measured by its SLA. If you look at any service today in any cloud, whether it happens to be Azure or Google or AWS, typically the services either don't give you any SLA at all, or they give you the SLA typically for high availability. Again, when we try to approach this problem, we step back and ask ourselves, again, a fundamental question. What are all the things that developers and customers really, really care about? And they care about performance, they care about throughput, they care about consistency, they care about availability, they care about latency. So this is actually the first service in the market that has published comprehensive SLAs that are backed up by Microsoft financially. So we actually had to change the entire Azure SLA page as a result of this service. So you can now see that basically, you're guaranteed that if you come in and you run your workload, you will get the consistency guarantees, you'll get the correctness, you'll get the high availability at the 99th percentile, and you get the throughput and the latency that you provision. These are just some of the snapshots, for instance, for some of the customers for various consistency models and what they observe. Guaranteeing the high availability, for instance, we're tracking availability at the per tenant level and per partition basis at the 5-minute granularity. And I will tell you, the engineering folks get woken up at 2, 3 o'clock in the morning if the SLA goes down before even customer will notice it. So we take them pretty religiously in that regard. This is something that is fundamentally the core principle of this service. No new capability will go into the stack if the SLA will be violated. And this is, again, this is showing the same customer with respect to the availability. For instance, they were running, again, the throughput requests, and their availability stayed at the 100% at all of the time. So one of the things is that what we enable customers to do is they can come to the Azure portal inside Cosmos DB, click on the metrics blade, and they can see actually their runtime statistics against the promised SLA. So you can come in, pick the latency, and you can see in the last 1 hour, last several hours, last 24 hours within the region, across the regions, what was the SLA and what was your actual runtime telemetry that you got. So this has been so far what I call the foundation of the house. Now the second thing that we've also made the decision about is that we decided to make the service multi-model. And the idea here was to try to meet developers wherever they are. So if you're building a polyglot app, chances are you're working with various data models like key value or documents or graph. So we wanted to enable this native experience and native integration with all these various data models. Behind the scene, actually, there is really only one data model, and we call it ARS, which stands for Atoms, Records, and Sequences. And all of these user-defined data models get actually translated to this ARS representation that is natively built into the stack, and then we scale the backend and do the partitioning and resource governance and whatnot. So it's very easy for the service then to go and onboard various other data models now and in the future as well. The other interesting question that I frequently get asked is, well, if, for instance, I have a document data model, but I want to also have a graph, do I need to keep 2 copies of the data? And the beautiful part is that you don't have to. So this is actually a sample code where I can connect to the same container of data and treat it as a collection of documents, and then using exactly the same client, I can look at it as if it were a graph. And that's actually a pretty powerful combination, looking at your data through various lenses and see what type of information can you extract out of it. The why part, I've already covered it. I'm going to go a little bit faster given the time limitation and given the hiccup a little bit. So let me go right now to another motivation. Why we also decided to go with the schema agnostic approach. This was also another key fundamental requirement that we've noticed, that modern applications, and particularly built in the cloud, tend to be anything but static. They evolve over time. So for instance, you can start out with one particular schema today, then you need to add more tables, you need to add new columns, you need to come up with a very robust approach to be able to handle these types of scenarios. And so as a result, the object model was designed to be completely schema agnostic and schema free. The difference here is that, for instance, if you take a physical object like a car, if you come into a relational data model, typically it will ask you to normalize it. With the Cosmos DB, we try to, again, go with the approach that will try to store the data as is. So, for instance, modeling the data in the relational way, you could, for instance, store it as such. In Cosmos DB, it will look something like this, where you can go and collocate all of the parameters of your data in one document if this happens to be a document data model. How do you query such a data? So in this case, this is an example of a SQL query. Remember, behind the scene, we actually represent all of this data using this ARS representation. It's humanly readable as a JSON representation, JSON document. So in this case, the input data may contain these 2 documents, which represent locations and countries with different headquarters. They can be represented as a tree. And then you specify a query, and as a result, you get back another tree, which humanly you can read it as yet another JSON document. And so, as I mentioned also, at the global scale, dealing with indices or schema management becomes actually, in some cases, conversation non-starter. So we've built this as a schema agnostic and fully indexable, the engine that indexes all of your data automatically. So in this case, for instance, given this data could be represented as a tree, and then we will go and automatically index it as such. How does it actually look like? Well, the indexes look like the following. It's basically a union of all of the document trees. And then you can basically go and consolidate them all into one and only keep the unique values that are idiosyncratic to each one of those documents. All of this structural information in the instant values are then normalized in this unifying concept of the JSON path. So it's an inverted index. It provides for the optimal write, query performance, and storage. So given the path, we can quickly identify the physical documents where the data is located and fetch them right away and then serve them. This is actually the frequency of the document frequency and the unique path lengths across the collections. It actually tends to be not that big. You know, if you think about it, one of the sort of frequent reactions people ask, oh my God, you take all of these documents, you consolidate and union it all. It must be the paths might be very, very large in volume. And it's actually really relatively not big at all. The index overhead in practice is also pretty small. So for those of you who are really interested in learning more about this, we've actually published a paper in VLDB called Schema Agnostic Indexing. So for more details, I highly recommend you read that there. So I will skip then through the physical index organization. I wanted to point out, so in the context of relational databases, the indexing structure is typically the B+ tree. In Cosmos DB world, we've done this collaboration with Microsoft Research to develop this indexing scheme called BW tree. And it's designed to be basically highly concurrent, lock-free, threads, never block type of indexing data structure. It's optimized for SSD. We structure the storage as a log, and we avoid random writes at all possible cost. There are 3 layers to this indexing structure: the log structured store, the cache, and the actual B tree, which is the serving layer. And again, I highly encourage you to read the paper to learn more about it. Let me go a little bit faster here. And this is actually a diagram showing highly concurrent page updates, for instance, with a classical B tree, where the inserts typically, if you have multiple threads trying to go and write to the same page, they typically will try to conflict and the threads will block. In the BW tree, it's basically implemented as delta updates. So you'll have the page and all of the updates that are happening. We have the mapping table with the page ID and the physical address, and any updates that are happening, we store them as deltas. And if, for instance, 2 threads are coming at the same time and they're trying to update and insert a new record, what will happen is that we'll just add 2 delta updates. They will never block. They will never conflict with each other. So this is the fundamental sort of design characteristic deltas between 2 approaches. Okay? And so forth. Let me go a little bit faster here. The timer is clicking, so I'm trying to accommodate so you don't miss any of your sessions. And this is the overview, the architecture of the actual query processing pipeline. So you have the SQL coming in. We also have the SQL flavor on Cosmos DB. And this is, again, to welcome all of the people who are familiar with the declarative language like SQL. The semantics is different by virtue of having a different type system. You know, fundamentally, one of the sort of semantics principles with ANSI compliant SQL languages and the engines like SQL Server is the semantics that comes with it. In this context, it will be different semantics by virtue of having a different language, slightly different language surface, and also the type system. You have basically the basic components of any query processing engine. You have the SQL compiler, you have the code gen, you have the query runtime, you have the actual query planner, which is the equivalent to optimizer, and then you have the hosting runtime to be able to host other runtimes in the case here, it's a JavaScript runtime and also the compiler, because we treat JavaScript as a first-class citizen inside Cosmos DB. And this is zooming in on the JavaScript integration within the database engine. Again, you can come and create your stored procedures, UDFs, using JavaScript itself, and it will natively run by virtue of us having the actual JavaScript hosting runtime. But the engine is very flexible, and it's not hard to imagine at some point in time we'll be hosting other runtimes as well. So this is, right now we're getting to the doors, opening the doors into this house. The multi-API approach, and again, the idea here was to try to add the native support for multiple APIs, formats, and wire protocols. So if you're coming from the MongoDB world and you want to use the cloud and you want to store your data in the cloud but not rewrite your app, you can do so. The interesting thing here is that, so today we support SQL, JavaScript, MongoDB, tables, Gremlin, and more APIs coming in the future. The key insight here, what does the strategy actually enable you to do? In many cases, your application, if it's built against an on-prem NoSQL system like MongoDB, you don't even have to recompile it. You change the connection string, it will point it to Cosmos DB, and it will work as is. You automatically get the better SLAs, lower TCO, all of the goodness of what Azure brings to the, to the table, and also without having to change your application at all. The other key insight is that all of these APIs typically come with a huge ecosystems built around them. So there is tons and tons of GitHub projects, libraries, SDKs, communities built around all of these on-prem equivalents. We don't have to rebuild any of that. They will work as is. We just need to make sure that the APIs are wire compatible, and then all of that ecosystems, they work magically and beautifully against the cloud and against Cosmos DB. You also don't have this lift-in, no vendor lock-in either, because in this case, if you can continue either still running it on-prem or in another cloud if you wish to do so, or you can come to Azure and run it with Cosmos DB. Lifting and shifting from on-premises to cloud becomes a lot easier. So another key insight that I wanted to share with you is that how do we specify, verify, and test a system like Cosmos DB? That's actually an art of itself. Working on this system in particular, I get to appreciate how much work it takes to operationalize a service that runs at such a scale. There's a very good quote, and I attribute it to Kyle. All happy databases are alike. Each unhappy database is unhappy in its own way. It's Kyle's Kingsbury quote, but it came originally from Leo Tolstoy. So highly recommend to read Anna Karenina book if you guys want to. So how do we run the service? We have weekly deployments of the entire stack worldwide. There are tons and tons of quality gates, everything from chaos testing, component and functional test coverage, automated performance, resource governance, consistency are running every 4 hours. We have about 16 hours of stress testing running every single day just to make sure that everything is operational. It's like Magic Factory across the entire globe. We also run the automated linearizability checker and Jepsen tests. We also run various types of other invariant checks. We have bots that are automatically going and fixing any nodes that are indicating that potentially they might go down or there's some abnormality. We have automated bots to identify those problems and actually try to fix them as well. We have a consistency tracking and reporting going over the live data, and this is to make sure that all of the consistency guarantees are intact because, again, there are SLAs, financially backed SLAs behind it. We run the Jepsen test, and this is one of the snapshots that I've taken. If you don't know about Jepsen, do read up on it. It's basically sort of the truth of the product when it comes to distributed systems, how to break your databases and identify these issues a priori. And this is one of the charts I wanted to show you, basically where we try to predictively identify faults. How likely is that particular node going to fault, and identify it proactively and try to see if we can salvage it early on. So in conclusion, I have a few minutes left. I wanted to put myself in your shoes. Every time I give these keynotes, it's a lot of information to digest, and it's different also, given also that it is the audience that is familiar with SQL, but not so much maybe with some of the technologies like these. I always say with the keynotes, it's challenging because 30% of the audience might be the experts, 30% know a little bit about it, and 30% might not have any clue. Hopefully, all of you sort of enjoyed it. But why should you care? I always say you don't get pearls without irritating the grid. Somebody tweeted the other day, and I really liked that tweet. It said, the world of data is divided into two groups, of those who use Azure Cosmos DB and those who will eventually use Cosmos DB. So I didn't say it, that person did. But the way I put it, there's a Darwin quote. It's not the strongest of the species that survives, nor the most intelligent. It's the one that is the most adaptable to change. And that's what we're trying to do, adapt to the trends that are emerging and also translate them very, very quickly into the product. One of the things I would encourage all of you is that we have this capability called Try Cosmos DB for free, where it's actually an experience. You can come in, you don't have to have Azure account, you don't have to have a credit card, you can just come in and experience the service. So rather than sort of listening to me also pitching it and telling you, try it out for yourself and see for yourself. The other thing is also, your childhood dream of finally going into Cosmos will finally be fulfilled. So, you could become a Cosmos DBA. But the key points to remember from today's presentation. Global distribution, horizontal partitioning, fine-grained multi-tenancy cannot be an afterthought. These things need to be built in from the ground up. Schema-agnostic database engine design is crucial for globally distributed databases. Again, create, alter, index when you're running across multiple regions, multiple data centers across the entire planet, becomes too rigid. Third is intermediate consistency models are extremely useful, and the customers can reason about them. They are pretty well intuitive, and you can make the right trade-offs. And with the SLAs that the systems try to give you, you guarantee the correctness of the approach. And the globally distributed database must provide these comprehensive SLAs. Fundamentally, we are in the service business, and I anticipate that trend to actually continue in other services in the entire industry to follow this direction. So the other things is that it is a hidden gem. I am very optimistic and passionate about this service. There's also another bigger message, and this is, I always say, remember the entire NoSQL movement was a counterculture movement, and I am being counterculture right now in this audience. But the question, really what it comes down to is that you ask a question of yourself, how would we build databases if we were starting today? Without all of the legacy and everything else, would we look at it differently? Would we look at limitations, constraints, biases, or whatnot? Would we focus on this, or would we try to focus on something like this? I am an optimist. And this, for instance, adding some creativity, adding some color. Sometimes it is okay to break rules. Sometimes it's okay to try different things. I put it, life is too short to build something nobody wants. So, if I really fundamentally believe if we focus on real pain points, not sort of nice to have, but really fundamental pain points, abandon the constraints, self-imposed dogmas, whatnot, we can change what it means to have a modern data system. And I call it creating a modern SQL, perhaps, I don't know. So I want to acknowledge the entire Azure Cosmos DB team who is working really hard. It's one of the most talented engineering teams I ever gotten a chance to work in my lifetime. They're really pretty awesome. And I want to thank all of you for giving me this chance to come and present here again. Thank you so much.